This is the start of the second tape, and we'll pick up where we left off. Remember, we were talking about the geometry bar and how the cooling rate decreases. Let me give you an example using the figures on page 64 of the handout sheet, what you might be able to do with this information. Let's use the left-hand side. This is the cooling rates for round bars quenched in agitated water and agitated oil. The heat transfer coefficient is greater for agitated water than for agitated oil, so you'll see these are a little bit steeper slope. And let's say for our example, maybe we could blow this one up a little bit on the left-hand side here. Let's say for our example that we have a 3-inch diameter round bar of steel, and we're going to quench it in water, and we would like to know what the hardness profile would be without actually having to measure the hardness profile. So for the 3-inch diameter bar, we draw a line across there, and where that intersects these curves, we can drop perpendiculars down to the axis, or if you want to, you can go up to the cooling rates that are up there. And what this tells us now, this is the temperature at the surface, hardness at the surface, cooling rate at the surface. This is at the 3/4 radius, this is at the mid radius, and then this is at the center. So what we're going to be able to plot here will be the hardness on this 3-inch diameter rod for 1.5 inches, and you would expect it to be symmetrical about this. So now we need to pick a steel. Let's pick two steels, and let's try a 4340 and a 1040. Same carbon content, but now differing in alloying content. We'll see a significant difference here in the hardness. So now we have these. We need these numbers. So this looks like it's at the surface, it's 3 millimeters. At the 3/4 radius, it's 8.5. At the mid radius, it looks like it's 13, and at the center, it looks like, what do you think, 16.57? 16.5. All right. Now, where's it going to be? Where's it going to be hardest? At the surface or at the center? Well, you're quenching it in water, that's going to cool quicker, so you would expect the surface to be harder than the center. If it's a material that has high hardenability, you're hoping that the surface, the inside, is going to be nearly as hard as the surface. So let's try this for the two steels that we have. Now we go on back up to the geometry curve, and at 3 millimeters, 1, 2, 3, what were the two steels we had? Let's see, 1040 and 1020. Let's go ahead and just list the values here. Surface, surface, 3/4, mid, and center. And now for the 1040 steel, at 3, we would have a hardness of about 37. At 8.5, we would have a hardness of about 27. At the mid radius, that's 13, so we would have a hardness of 25. And at the center, which is 16.5, we would have a hardness of about 24. So if you take a look at those hardnesses for the 1040 steel, we'd have 37, 27, 25, and 24. And now if we plot those, 10, 20, 30, 40, 50. I don't know if we'll get any higher than that. Then, let's see, this is 10, 20, 30, so the surface would be 37. At the This is going to be the mid-radius. This is going to be the 3/4 radius. At the 3/4 radius, it's 27. So it's dropped down. At the mid-radius, it's 25. And at the center, it's 24. So if we'll use little circles for the 1040, the hardness profile across that 3-inch bar would be given in that way. Now we're making a prediction, and it turns out the prediction will be pretty darn good. Now let's try for the 4340, and now at 3 millimeters for 4340, it looks like we're at 57. Wow, so the initial hardness is substantially greater. At the 3/4 radius, oh my goodness, we're still up at 55. At the mid-radius, we're at 13, and it looks like maybe 52. And at the center, we're at 16 and a half. Looks like we might be 50. Well, I guess I read the 4140, but so this is 54, and this is maybe 53. So we'll see that for the 4340, it's going to be substantially harder than it would be for the 1040. So we're at 57 to begin with. 4050, we're up here. At the 3/4 radius, well, we're not going to go very far from up there. And basically, it has the same hardness almost across the whole bar. So we would call this a through hardening steel. So, and this shows you the effect of alloying elements. Same carbon. This has nickel chrome moly. It's a chrome moly nickel steel, and this has a little bit of manganese. So there's a huge difference in the hardenability. So if you wanted a fully hardened bar, you'd want to choose some alloy steel, not a 1040 steel. So that's how you can use the geometry data and that hardenability data to help yourself make predictions. Now there's one other heat treatment that I was going to talk about, and that is precipitation hardening. The precipitation hardening process is common in aluminum alloys. And one of the common aluminum alloys is 6061. That's a magnesium silicon alloy, commonly used for window frames and door frames. In the solution treated condition, it's designated as T6. The first step is a solution treatment, and if we were to look at the phase diagram for this material, it's a eutectic system. This is alpha. This is going to be liquid. This is the melting point of aluminum, 660 degrees centigrade. And so the solution treatment is under the eutectic, but as high above this phase boundary as you can. So this would be the solution treating temperature. So the first step is to solution treat, puts alloying elements in solution. The second step is quench. Now this is a real interesting step, and because the results are quite different than what happens with martensite and steel. We quench. This traps alloying elements. And there's no eutectoid transformation. Aluminum's face-centered cubic, and so in fact, after you've quenched, the material is soft and ductile. The aircraft industry uses this for their rivets. They solution treat them, quench them, store them in a refrigerator till when they're ready to use them, put them on the plane, and then they allow them to strengthen naturally during the process as they warm up to room temperature. Aging is a reheating process where now we're going to distribute the alloying elements, and actually the strength is going to increase. So strength will increase during the aging process. Similarly, there's no free lunch. The ductility will decrease. So if we plot strength or hardness versus aging time, what we will find out is that there will be an increase to some maximum value if we do it for higher temperatures or lower temperatures and longer times. So temperature would decrease as you would go here. So T1, T2, T3, T1 is greater than T2 is greater than T3. So that's another way that you can strengthen materials. We're also responsible for mechanical testing, and I think this will be a little bit a review of what mechanics of materials, where you probably have talked about a tensile test already, but we'll just touch on a couple of things associated with a tensile test. This is probably the most universally used test in terms of collection of data. Engineers will look at strength and ductility properties almost as a first cut for many types of designs. And in the tensile test, we have a uniaxial bar, we have a reduced cross-section, we put a force on, and we measure that force. We know the cross-sectional area, and we convert that to stress. This is the engineering stress-strain diagram, where we're going to divide by the engineering stress compared to the true stress, where you divide by the instantaneous. The strain is equal to the change in length over the gauge length. And if you plot stress versus strain this is an example of a ductile material. This has a upper and lower yield point. This would be an example of a steel material. This is the yield stress. This is the tensile stress or ultimate tensile stress. This would correspond to the breaking stress or the fracture stress, where the breaking stress is P over A0, the fracture stress is the true stress, P over the final area. Now for engineering applications, this is the elastic portion, this is the plastic portion. Once it starts to plastically deform, if we loaded it up to this point and unloaded, it would follow the same slope, and we would have some permanent plastic strain. In other words, the bar would be longer than it would be than we started. The slope of this elastic portion, the stress divided by the strain, is equal to the modulus of elasticity, or for polycrystalline materials, Young's modulus. So the modulus E is equal to the stress divided by the strain. That comes up in a lot of static analysis. The modulus of elasticity is a measure of stiffness. Very similar to a spring, F is equal to Kx, where K is the spring constant, the modulus is the constant connects the stress and strain. Once the material starts to plastically deform, the stress is no longer recoverable. And while this one looks fairly easy to determine what the yield strength is, for many materials it's not nearly so sharp. So people use a 0.2% offset yield stress. And if you go to the second page, page 31 here, there's an example for an alloy showing the 0.2% offset yield. Here's the elastic portion, would give you the Young's modulus, and now you would say, well, where's the yield point? If 5 people did that, you'd get 5 different answers. So what engineers have done is to find a 0.2% offset yield strength, and you come 0.002 strain units, draw a line parallel to the modulus, and where that intersects the yield locus, that's going to be your 0.2% yield stress. And most of the values you see in handbooks would be that number. It lets your lab and my lab have the same number. and not try to determine where it would be on that value. We can also talk about the ultimate tensile strength or the tensile strength. The ultimate tensile strength is defined as P max over A0. And ductility, there's really two ways of talking about ductility. One's the change in length, and that's the final length minus the original length over the original length or gauge length times 100. And that's a good measure of uniform deformation. Another is the percent reduction in area. Percent reduction in area is A0 minus the final over A0, again times 100. And that's a good measure of the amount of localized deformation. So those are two measures of ductility. If you go back with me to page 31, you can see on the top portion of it a series of stress-strain curves, and these series of curves, I was just trying to enlarge it a little bit. There we go. You can see from magnesium to a quenched and tempered steel that the strengths vary from 15 to 240. If we just take a look at steel, for example, we can find that structural steel can be about 30, and if you go up to a nickel alloy steel, it can be 240. So there can be an 8-fold increase in strength by heat treatment and alloy composition. Correspondingly, you see that there's a great variation in ductility from 25% to something less than 8%. Now, another mechanical property that is important is the measure of how a material behaves under impact load. The tensile test is a real good measure of the behavior of a material under a static load. The sinking of the Titanic is a nice example of materials that were strong enough and had sufficient ductility. They didn't know enough to evaluate them for their impact characteristics. And once it crushed into that iceberg, the material behaved in a brittle fashion, so a number of cracks opened, not the 300-foot gash that was first originally thought. Now, for an impact test, if you look on page 33, one of the common impact tests is a Sharpie V-notch test. There's a specimen, a centimeter on edge. There's a notch. You load a hammer or a pendulum to a certain position. You drop it through the material. It strikes opposite the notch, putting the maximum tensile force here. The energy absorbed is a measure of the material's toughness. The energy absorbed, if you plot it versus temperature, it might look something like this. This is called the upper shelf. This is ductile and tough. This is called the lower shelf. By the way, the energy in foot-pounds can also be in joules. This is the lower shelf, and this would be brittle behaving, not tough. And people use this test to determine the DBTT. That's the ductile to brittle transformation temperature. Generally speaking, you want the ductile to brittle transition temperature to be lower than the temperature that your material is going to be used in. Texas, for example, we don't have to worry much below 10 degrees, 15 degrees. But if we were putting a pipeline in Canada or Alaska or upper Midwest, we'd want to have the ductile to brittle temperature at minus 50 or minus 60 degrees to ensure that the material would behave in a ductile fashion. You can determine the ductile to brittle transition temperature by a number of ways. This might be the 50% brittle, 50% ductile appearance on the fracture surface, and where this intersects the curve and drops down, this would be and intersects the temperature axis, this would be the ductile to brittle transition temperature. So you would, generally speaking, want to stay, for your application, you'd want to be above the ductile to brittle transition temperature, because the material fails brittly in this region, fails ductily, and has some toughness in this region. If you look at the lower portion on page 33, there's a variety of different curves. Body-centered cubic materials undergo a ductile to brittle transition temperature. Face-centered cubic materials don't. And that's why face-centered cubic materials have cryogenic applications. Stainless steels, nickel, aluminum, copper are used at low temperatures. And ceramics and some polymers also undergo a ductile to brittle transition temperature. And a third type of test is a fatigue test. There's a couple of kinds of different fatigue tests. The one that we're concerned with would be called a SN type of approach, where you plot stress versus the number of cycles. It's usually in a log, and the curve for a ferrous material might look something like this. This is called a knee. We have failure here, and we would be safe here. This is called the endurance limit. And what is said is that if you're below the endurance limit, you don't need to be concerned about failure. Now, actual fact is that if you have stress risers, corrosion, wear, there are a number of things that can lower that endurance limit. And also, I ought to really be honest, shouldn't I? This is really a band region, and there is some statistical nature to the fatigue process, where there are some specimens, a few going to fail on the high side, some going to fail on the low side. Usually you have statistics. If you want 50% chance of it failing here, that would be the solid line. This region in here is called high cycle. High cycle, and that's low stress. This is called low cycle, and it has much higher stress. Lots of plastic deformation on each cycle, or there can be. Under the low cycle fatigue, materials can fail at stresses below their yield strength, but because of the cyclical nature, you can induce a crack, crack can grow, and final failure will occur. The fatigue initiates at the surface, so it's a surface phenomena, can be at a hole, a stress riser, a variety of different steps. So the process is initiation, propagation, and some people include a slow and a fast step, but propagation and then final failure. And there are some techniques where you can use fracture mechanics to monitor cracks that are in materials and don't have to take something out of service because there has a crack in there. There's steam generators, airplanes, railroads that move, fly, and generate electricity with cracks in, but they are safe to use. There's a difference between ferrous and non-ferrous metals. If we take a look at steel, most steels typically have, can we flip this on? There we go, great. If we take a look at the ferrous materials, they typically will have an endurance limit, they'll have what's called a knee. This is the low cycle high stress. This is the high cycle lower stress. For non-ferrous materials, which aluminum is an example, there often seems to be no endurance limit. So you need to really test out to the number of cycles that you're going to use. And the final two things that we're going to talk about will be the grain size and briefly on composite materials. Grain size can be important because it is important. As grain size decreases, the strength will increase. And there's an expression called the Hall-Petch equation, which says that the increase in strength increases by the square root of the grain diameter, where D is the grain diameter. And one of the ways of determining the grain size is from an ASTM expression, which says the number of grains in some unit measure, in this case 0.06 millimeters squared, is equal to 2 n to the minus 1, where n is the grain size. And let's say, for example, let's say that there would be 35 grains at 0.0645. So we'd have 35 is equal to 2 n to the minus 1. Go ahead and solve that, huh? You can take the log of 35, or log of 35 is equal to the log of 2 to the n minus 1, and that's going to be n minus 1 times the log of 2, log of 35, and you can go ahead and solve that for n, where n is the ASTM grain size number. Now, if n is small, 1 or 2, that's large grains. If n is large, and large would be 10 or 11, that is small grained material. So this would be strength increases as the grain size gets smaller. There's another way of determining the grain size, and that's illustrated in the equation that I have on this sheet. And L here is the average linear intercept. And the way this works is you have a length of line divide by number of intersections, divide by the magnification, and that gives you an average linear intercept. And if you assume that you have spheres, the D for spheres is equal to 1.5 L bar. So you can actually get a grain diameter from that grain size. The last thing that we're going to talk about will be composite materials. And some examples of composite materials, the kinds of things that might be helpful to you, would be application of the rule of mixtures. This says if two phases or two properties are not mutually dissolvable in one another and are independent, we can describe them by a sum of the individual properties. For example, the density. If we have two phases that aren't dissolvable in each other, then they would be F1 row 1 plus F2 row 2, where that would be the fraction, this would be the density, fraction, and density. So the Fi are the fraction of the phases present, and rho I is the property of the phase that's present. You can do the same thing with the modulus of elasticity for the material also. And I was going to conclude just with this example for the modulus of elasticity for a composite material and have you think a little bit about how it would be in either parallel or perpendicular type of format. If we've got two phases or two components, like say graphite epoxy or fiberglass polymer matrix, then it's going to be F1 E1 plus F2 E2. And if the fibers have a higher modulus, you can see really why you would want to have a high volume fraction of fibers in there. Now, how's it going to be parallel or perpendicular? Well, if we put a load on here parallel, what's going to be constant? It's going to say that the strain in the fiber is going to equal the strain in the matrix is going to equal the strain in the composite. And if we do that, that says that the modulus of the composite is equal to F1 E1 plus F2 E2. And if this is the fiber, and if that's a large number, and this is a strong modulus, that's really going to dominate. But now what happens if we take a look at it perpendicular, and what's the modulus going to be? Well, the strain's not going to be constant. In this case, we're going to have the stress in the fiber is equal to the stress in the matrix is equal to the stress on the composite. And if you work through the modulus in that way, we'll find that the modulus is much more sensitive much more sensitive to the matrix. And while the higher volume fraction will help you some, you can see here really that if you're going to pull this way, the fibers aren't going to contribute anywhere near as much as the matrix. So here you're going to have a modulus that would be much closer to the matrix value than you would for the perpendicular, than you would in the parallel value. Well, this has been a tremendously rapid summary of material science. We've covered a broad range of things today. We've looked at corrosion, we've looked at phase diagrams, mechanical properties, cold working, annealing, some thermal properties, and looked at crystalline materials. There will be a evening question time coming in a couple of weeks. I would strongly encourage you to work some of the problems, bring some questions there, and then we can deal with those specifically at the time. Thank you very much. Good luck.